Okay, so what I want to clarify is the relationship between the advertised window and the sequence number. So the requirement is the size of the advertised window should be at most half the sequence number space. So if the sequence numbers, for example, um, uh, if the sequence numbers, for example, range from 0 to 15, that's the maximum sequence number, 15, right? So the advertised window size has to be less than or equal to 15, the maximum sequence number, plus 1 over 2, which is 8. So which means the number of bytes that you can send, each byte has a sequence number, right? There is going to be at most 8. That's the advertised window size. Okay, so in general, that's why as I have there, the advertised window size can be at most the sequence number range divided by 2. Okay, now the proof we are going to look at is it's kind of a contradiction, proof by contradiction approach. In order to prove this, let's say, why can't the advertised window be as simple as this? Of course, this is not a solid proof. We are going to just prove using an example. So let's say the advertised window space is a sequence number range -1 and a sequence number range is going to be, let's say, sequence number range is going to be up from 0 to 7. Okay, so we have 8 sequence numbers. Now let's say I send packets with or bytes with sequence numbers 0 through 6, because the advertised window size is sequence number range -1, so that this is 7 bytes. That's the maximum we could send, right? Advertised window is sequence number range -1. So let's say all those 7 bytes 0 through 6 make it to the receiver, and the receiver sends the acknowledgements for them, and let's say all of those acknowledgements get lost. So this is at the source side, and the destination side, this is going to be bytes 0 to 6, right? Or packets with sequence number 0 to 6. So either way you can look at it. So now the destination has acknowledged all of them, and the acknowledgements get lost, right? The acts get lost. So what happens? The source will time out and retransmit the same window 0 to 6, the first 7 bytes, but the destination is expecting, because the destination knows the range of sequence numbers 0 to 7, so it expects a 7 of the first session, of the first kind of what do you call, first set, and then it expects bytes 0 through 5 of the second set. So this is from set 1, and then it expects 0 through 5 of the second set. So totally this is 1 byte here and then 6 bytes here, so 7 bytes. So this is what the destination is expecting, because it has already got 0 to 6 on the first set, so it's expecting the last byte from the first set and then the next 6 bytes from the second set, so that can make up 7 bytes. But all these 7 bytes were sent for set 1, the first set. Okay, so these are the 7 bytes that were sent 0 to 6. So what happens? This source is going to retransmit these 7 bytes from 0 to 6, and the destination is expecting this. Destination is expecting this set. So the destination will end up assuming these bytes 0 through 5 here as these bytes that it is expecting. So that's what is meant by a replay error, because these are actually corresponding to set 1. All these things correspond to set 1, and they have been received and the destination is acknowledged for them, but the source is retransmitting the same thing. But the destination is expecting 0 through 5 from this set, the second set of bytes. So it's going to assume, end up thinking that it is receiving 0 through 5, but of course 7 has not come yet, so that's what the receiver will think, and it will think it has got bytes 0 through 5. So that's a replay error. So to avoid this, we need to have, that's why the advertised window size should be at most half the sequence number range. So let's look at kind of why it will work, again based on, through an example. Let's say the sequence number range is 0 through 15, so we have 16 numbers, and the advertised window size is only half of it, which is 0 through 7. Okay, so now if let's say again the source has sent the bytes 0 through 7, and the destination has received them, and it is going to, it has sent the acknowledgement for them, and the acts get lost. But these are bytes 0 through 7 of the first set, and the destination has received them, right? And then of course you have bytes 8 through 15. Again, they are of the first set because there's no wraparound yet. Okay, we have 16 bytes that you can send as unique sequence number within this set, so there's no wraparound yet. So if those 8 acknowledgements get lost, the source is going to retransmit 0 through 7, and if they come here, the receiver is going to think that because they come out of range, because receiver is expecting bytes 8 through 15, and the source has retransmitted bytes 0 through 7, so the receiver is going to think them as duplicate packets, and they're going to be dropped, because it knows what it's expecting. It's expecting 8 through 15. In this case, it was expecting 7 and 0 through 5. So that's why when 0 through 5 came, it considered them as new bytes that it is receiving for set 2. But these are actually the ones that have been retransmitted. And so in the previous case, the receiver accepts them because it was expecting them 0 through 5. Okay, so when the 0 through 5, the retransmitted version came, it thought it is a new thing, because there's no way you can distinguish a retransmitted packet from an original packet. But here the destination is expecting bytes 8 through 15, so when it gets 0 through 7, it could discard them as something that is not expected. Okay, so so that's why this is the worst case, that the entire window of acknowledgements have been lost. So if this happens, you should be still able to detect duplicate packets and accept only packets that are sent in the valid range. Okay, so basically, as you see here, this is the entire window of sequence numbers 0 through 15, and half of it is your advertised window space. So even if the entire window gets lost, you can still get around this situation. Okay, so that's why the advertised window size has to be at most half of the sequence number range. Okay, now the next issue is about this keeping this pipe full. If you do not keep the pipe full and send just one data packet and wait for the acknowledgement for that packet, you will wait for the entire round trip time, which is basically the time since you send the data packet and until you get the acknowledgement. Now, of course, we need to do better because we are not using the bandwidth efficiently. If the data size is just 1000 bytes and the bandwidth is say 8000 bytes per second, then essentially, and if the RTT is also 1 second, then essentially you are sending only 1/8 of the bandwidth. So if you want to maximize the bandwidth usage, which is basically the throughput, we want to send as much as what the bandwidth can allow. So that's why we will try to send what is called the delay bandwidth product amount of data. Okay, because the bandwidth is in units of bits per second, which you could also say bytes per second, and the RTT is say in seconds, so seconds times bytes per second is going to be bytes. So this is going to give you the number of bytes that can be on the channel, or before that, the number of bytes that can be sent from the source until the acknowledgement is received. Okay, so this is also the number of bytes that can be on the channel at any time instant. Okay, because until you get an acknowledgement for them, right? So this is what is called the volume of the channel. Okay, so the delay bandwidth product basically gives you the number of bytes that can be on the channel at any time instant, and it's called the volume of the channel. Okay, and so if you want to maximize the bandwidth usage, you want to send according to this RTT bandwidth product. So, but of course, the destination should have the capacity to accept everything that you send, right? So that's why you want to make sure the advertised window size is at least the RTT times bandwidth product. Okay, but you don't want it to be because if you calculate the number of bits that you need to allocate for the advertised window size, you need to go for the minimum, in the sense that because if this is what the RTT bandwidth product can allow, there's no point in having a size that is larger than this, right? So that's why we always say the advertised window size is equal to the RTT bandwidth product, because you're not going to send anything more than the RTT bandwidth product. Okay, so if you want to now find the number of bits that you need for the advertised window size, then you have to take the logarithm of the RTT bandwidth product to the base 2. So I'm going to indicate like this: log 2 logarithm of RTT times bandwidth product to the base 2. Okay, so that's the number of bits you need for the advertised window size, because you need to advertise that you can accept that many bytes. That corresponds to this RTT bandwidth product. Now that is what is called keeping the pipe full, because that is the number of bytes that can be on the channel at any point of time. The next issue is this maximum segment lifetime, because once you put a segment on the internet, it propagates towards the destination. It's buffered there, and it is processed by the application, read from the transport layer buffer, and all these things happen. So until then, no other byte should have the same sequence number as that of the bytes present in this particular segment. So which means we want to actually kind of delay the wraparound of the sequence number, because you know in TCP the sequence numbers range from 0 to 2 to the 32 2 to the 32 minus 1, right? So we don't want a byte sent with say sequence number 0 to roam around in the internet, and then after sending the byte with sequence number 0, we send byte to sequence number 1, then sequence number 2, and so on all the way to this 2 to the 32 minus 1. And then what will happen if you're not say using options to extend the sequence number range? You would end up sending a byte with the sequence number 0. And at that time, if the byte that we had earlier sent with the sequence number 0 is still roaming around in the internet, or it is in the transport layer buffer, it has not been cleared yet, what will happen? The receiver may end up getting 2 bytes with the same sequence number, right? So that's why we want to make sure that as long as a segment is alive, no other segment, basically no other byte, has the same sequence number that is present in this particular segment. Okay, so that's what we mean by maximum segment lifetime. Okay, so as long as the segment is alive, we do not want, because the segment is composed of bytes, right? The segment has the data portion, and it has all bytes in it. So, and we know in TCP each byte has a sequence number. So we do not want any other byte to have the same sequence number as that of a byte in this particular segment. So which means we want to associate each segment to have a maximum segment lifetime until which there is no wraparound of the sequence numbers. Because if the sequence number if the sequence numbers wrap around, then there will be 2 bytes with the same sequence number, right? So we don't want that wraparound to happen within the segment lifetime. After that, it could happen, which means whatever the segment we inserted has already been consumed by the application. So this wraparound has to happen, but we do not want it to happen within the segment lifetime. Okay, so that's why we associate what is with each segment what is called a maximum segment lifetime, until which a wraparound of the sequence number should not take place. Okay, so okay. Now at what rate we can insert bytes, that's given by the bandwidth, right? So the bandwidth indicates the number of bytes that can be sent or inserted per unit time. So which means all the bytes that we insert onto the channel should have a unique sequence number. It cannot be for all the time, but it has to be until what time? It has to be until the maximum segment lifetime. So for the duration of the maximum segment lifetime, all the bytes that are inserted onto the channel have to be of unique sequence numbers. Okay, so that's very important. For the duration of the maximum segment lifetime, the bytes that are inserted onto the channel need to be of a unique sequence number. So we need to find how many bytes need to have a unique sequence number, right? So that is given by, that's what is given by the MSL bandwidth product. Maximum segment lifetime times the bandwidth. Because the maximum segment lifetime again is in seconds and the bandwidth is in bytes per second, so the maximum segment lifetime times the bandwidth is going to give you the number of bytes that need to be on the channel with a unique sequence number. Okay, so the logarithm to the base 2 of this is going to give you the number of bits needed for the sequence number space. Okay, so the logarithm of the MSL times bandwidth product to the base 2 is going to give you the number of bits needed for the sequence number space. Okay, so these two designs, these two things that we discussed, the number of bits needed for the advertised window size, the number of bits needed for sequence number space, this formulation will be very useful if you are going to design your own transport layer protocol. Of course, for the standard TCP, we know that the sequence number space is 32 and the advertised window space is 16 bits, 32 bits and 16 bits, and you can extend it as we discussed in class using the options. But if you're going to design your own transport layer protocol, for which you also need to provide all these characteristics, this is the way you could compute the number of bits needed for the advertised window as well as the number of bits needed for sequence number space. Now you have to be careful here. This is again need not be the number of bits needed for the final value. Why? Because we have another requirement which I didn't tell yet, which we discussed but I didn't use it yet. What was the requirement? The advertised window size has to be at most half the sequence number space, the one that we discussed in the beginning, right? So which means the sequence number space has to be greater than or equal to twice the advertised window size, just cross multiplying it. Okay, so your number of bits needed for a sequence number based on the maximum segment lifetime is this, and the number of bits needed for the sequence number, so this is actually based on, if you want to say, I can say this is the first one is based on the maximum segment lifetime, and the second one is based on the advertised window size. Okay, is based on advertised window size is what? Logarithm to the base 2 of twice the advertised window size. Okay, now we know the advertised window size is 2 times the RTT times the bandwidth product, right? So the sequence number, the number of bits needed for sequence number space based on advertised window size is logarithm of twice the advertised window size, which is log of 2 times the RTT bandwidth product. Okay, to the base 2, of course. Now what is the final value for the number of bits you need for the sequence number? The number of bits needed for the sequence number would be then the maximum of the number of bits that you encounter based on the maximum segment lifetime, and based on the advertised window size. Okay, so actually if I put it the other way, based on the advertised window size or based on the MSL. So that's what is actually shown in the slides in that formula here. It is 2 times the RTT bandwidth product log to the base 2. That's based on advertised window size, or the maximum segment lifetime times the bandwidth to the base 2. So that's based on the maximum segment lifetime. So the final value that you need to use to find out the number of bits allocated for the sequence number space is the maximum of these two. Okay, so this is the kind of theory behind the problems, and we'll then now look at the problems in another video.